All right, super. Welcome, everybody. My name's Sam Burden. I'm an assistant professor here in electrical and computer engineering. And it's my pleasure to introduce you to Professor Ram Vasudevan. Ram's a close friend and a collaborator and an excellent colleague. We know each other from our grad school days at Berkeley, where he did his PhD and also his undergraduate degrees. He did a postdoc at MIT with Russ Tedrake, which if you've been following the Colloquium, was here presenting last week. And since then, he's been faculty in mechanical engineering at University of Michigan and in their relatively newly formed Robotics Institute. He's won a number of awards, NSF Career Award and ONR Young Investigator Award recently. That was a big win for Ram in the last year or two. And then he also has multiple best paper awards from robotics conferences, controls conferences, an oceans conference, which I assume has to do with water in some capacity. I have way too many personal anecdotes to share about Ram, so I'll just pick one that was my favorite, which was the week we spent driving across Europe following a volcano eruption that stranded in Iceland that stranded us in Sweden. So it was a very intimate trip with 5 of us crammed into an Audi A5, barreling from Stockholm to Madrid so that we could catch one of the only flights home. Thank you to the, the Pyrenees that blocked the smoke cloud so that we could exit the continent.
Apparently, yeah.
Apparently. Anyway, I couldn't think of somebody I'd rather spend 7 days in a car driving 3,000 kilometers than Ram. So with that, I'd love for you to take it away, Ram.
Yeah, thanks for the invitation and thanks for that story. It's our wives are slowly becoming more and more tired of that story, and it's slowly aging us as well. So it's funny to hear that. And yeah, it's great to be here. I was telling Sam, it's like you guys have a bunch of heavy hitters and then me. So this will be the boring talk. It'll warm you up for the rest of the talks. You can find a PDF link to my talk down here at this tiny URL thing. And throughout my talk, there's a bunch of videos and whatnot. So, videos, Zoom and videos don't necessarily play well with one another. There's also a bunch of YouTube links to those videos. So if you find yourself wanting to see more, click there and you'll be able to find that. So with that, let me start off by thanking all the students who are actually the ones who are doing all of the fun, heavy lifting. And today, the thing that I'm going to be really speaking about is how can we make robots more autonomous? And the way that I like to contextualize that in a way is to start thinking about how hard robust autonomy is. And probably the simplest or most complex example of robust autonomy is humans driving. I mean, it's not autonomous, but it's sort of an idea of just a particular target application that a lot of people are interested in. And the way to try to understand just how difficult it is by looking at statistics. And these are beautiful stats from NHTSA from the 1920s all the way up until 2014. And on the y-axis here is the number of fatalities per 100 million miles driven in the United States. And what you'll see is that number is in single digits, basically all the way down to 2010, where that number is 1 fatality per 100 million miles driven throughout the United States. And that's per year. The statistic is incredible, especially when you think about just how much driving we as autonomous vehicle or roboticists have done. And that number, maybe is best understood by looking through the lens of Waymo, which is probably an industry leader at this point. They've driven, starting in 2010 until now, about 10, maybe 11 million miles. Most of that is in Glendale, Arizona, or in Southern California, or maybe Northern California. But frankly, it's not Michigan driving. And what we see is, they just haven't driven as much as a human being drives in order to, even get to 1 fatality. So we really don't have great numbers on just how well they're doing, although there have been some recent papers, and I shouldn't chastise Waymo too much. They've been trying to publicize just, how they've been thinking about this problem. But for us, at least as researchers, what we want to try to do is to develop techniques that can maybe get us beyond sort of just going out on the road and driving and seeing, if we can develop theorems about how robust or how autonomous our systems can become. And really, the goal of this talk is to develop sort of control mechanisms or an idea of how to control these systems that doesn't just work for autonomous vehicles, but can generalize across a bunch of different systems like walking robots or quadrotors or an armed robot. And to try to understand just why this problem is difficult, that is controlling these types of systems, one way to think about it is thinking about how a researcher or even someone like Waymo thinks about doing planning and control for these types of systems. So one way to visualize that is, I have my car here, and we'll sort of see this picture maybe over and over as we go along the talk. we have our car here, and we may have an obstacle. And if we wanted to try to do receding horizon real-time control for this blue car here, well, the way that this is typically done is that people discretize time and they generate a trajectory by using some type of optimization, which discretizes time and then uses a discretized dynamics while doing optimization in order to generate a safe trajectory. And the challenge here is that may generate a trajectory like this. And the question is, does that actually represent reality? And really the only theorems that we have that tell us if these types of representations are good or not is that as we improve the discretization quality, we expect or we hope that our solution gets closer and closer to reality. And so that may be, passing along these lighter and lighter lines that get closer and closer to this red car. And eventually, we may think that we're over here at this green dotted line, but in fact, in reality, because we've chosen a really poor discretization time step, we actually may be at this red line that is actually an unsafe trajectory when realized in the real world. And so fundamentally, there's this problem that we have, which is when we have these green trajectories over here on the left-hand side, we've discretized time maybe not very finely, and we have a coarse representation. That coarse representation may allow us to solve an optimization problem really quickly, and that may be a good thing when we want to do receding horizon planning. But on the other hand, that may not actually represent safety in a reasonable way. And so there's some fundamental trade-off between model accuracy or optimization fidelity versus what we're able to realize in reality. And that trade-off is something that as autonomous vehicle engineers or as roboticists controlling general systems, we're uncomfortable with, and we want to see if we can develop a way to overcome that challenge. Typical, sitting on top of all of this is the challenge of model fidelity. So, in addition to representing the dynamics of the vehicle with, a high quality discretization, we also have challenges associated with, for example, in the vehicle context, representing friction or representing different types of scenarios and having a model of the vehicle itself that is accurate. And so what this talk is really going to be about is trying to address these triumvirate of challenges by using infinite dimensional representations. And what this is going to do is allow us to transform nonlinear models into linear ones. And the challenge, at least in this talk, that we're going to try to address is how we can utilize these linear models in infinite dimensions in a way that is actually accessible to doing real-time planning without sacrificing performance or safety. And the first portion of this talk is going to be some work that we've done recently that's called Reachability-based Trajectory Design. And it can make a nice trade-off between performance and safety where we don't have to sacrifice either of those things while being able to do real-time planning. And that's going to allow us to do autonomous control of a bunch of different systems. And on the other side, we're going to talk about some work that we've done in the soft robot world, which is using another type of infinite dimensional representation of dynamics that's based on the Koopman operator. And that's going to allow us to control soft robots and actually allow us to do things that we haven't actually, or people in the literature haven't been able to do with soft robots to date. And so it'll turn out, and as I warned Sam, I have a lot of slides. Chances are I won't be able to get through all of them, and I apologize in advance. So I thought I would just front load the talk with a few videos illustrating how these different algorithms work. So the first portion of my talk is going to be about this RTD algorithm. So let me walk you through how that looks on a bunch of different examples. So we're going to see these videos a few times here. So on the left-hand side, you're going to see a robot planning view, bottom camera on the robot. On the right, you're going to see a real-world scenario. And this is in my lab when we used to have a lab before COVID. And on the left, what you're going to see is a bunch of waypoints that are essentially generated by some high-level planner. And we're going to have these obstacles, which are represented or detected by the vehicle at runtime using a planar LiDAR that are being drawn in red. Our robot's footprint is going to be in blue. And we're going to generate these reachable sets that are going to be control parameterized. And they're going to be basically selected at runtime. And we're actually going to be doing optimization to select that reachable set at runtime in order to reach that waypoint. And I'll describe how that algorithm works as we go through the talk. But this is what it looks like, at least while running on our robot here. So you're going to see, and again, if you'd like the sort of unfiltered video with it moving sort of nicely, go ahead and take a look at that YouTube link down there. But the cool thing here is that it's all happening on board the platform. It's all happening in a receding horizon way, and it can deal with sort of these types of environmental situations without any difficulty. The interesting thing is we've actually extended this work to a bunch of different platforms. So this is a collaboration with the University of Sydney, where we're essentially running a taxi service for them. And here we have our vehicle platform. It's an electric vehicle platform that's operating on their campus. And it's actually going from point A to point B and actually avoiding people and actually doing real-time planning here. And we can say nice things about the safety of this platform. Again, you can check out the YouTube link down here. The cool thing is this algorithm doesn't just work for these sort of vehicle platforms. It can actually work for quadrotors. And that's actually what I'm going to show next. Ooh. And here we go. So there's a quadrotor. And again, this is now, again, doing this type of trajectory design. You'll see the quadrotor in a second. It's over here. And you're going to see sort of us doing the optimization on board that quadrotor platform in real time. Can't go much faster than about 1 meter per second in this space because of the size of the lab. But you're going to be able to see sort of fun things happening here where we can even accommodate things like moving obstacles. And I'll sort of jump to the end to show what that looks like here. In this instance, we're just receiving predictions of what pedestrians are doing, but we can accommodate those predictions and still say something about the safety of this quadrotor. And again, it's doing receding horizon planning with an optimization algorithm running on board the platform where we can say something about the safety of this platform. And it can accommodate things like aerodynamic effects, et cetera, inside of its reachable set while doing planning. The cool thing is when most people see this kind of reachable set stuff, they say, well, look, this works really well for low dimensional models. What about more realistic models? Here's an example of us doing the same type of thing with a 7DOF arm. So this is a 14-dimensional sort of state space model. We're generating, in this context, reachable sets that are constructed online. And actually, this is going to be what I'll speak most of the talk about. And again, we're doing sort of planning through these really sort of complicated scenarios for manipulators because these obstacles are very thin, which tends to be a problem for most optimization-based control design algorithms. The cool thing is, and hopefully we'll see it, this can, again, do receding horizon planning. It's a dynamic obstacle that's just detected at runtime. And you'll see that we're able to nicely avoid that. And the amazing thing is that the same strategy extends to even higher dimensional robots. So this is Cassie in our lab. This is a 32-dimensional model where we're constructing a reachable set for it. And actually, it's doing real-time planning on board. And again, generating these reachable sets that it can say something about safety with respect to. And finally, sort of the really cool application that we've now recently been able to do is actually apply this to doing prosthetic control. And let me show what that looks like. Can you guys hear the volume here or no? Sam, yes, no, okay. So what this work is doing is actually doing prosthetic control, but now we have a set of predictions of what a human is going to do after a stumble occurs. And we can take that entire set of predictions and actually generate an input for the prosthetic that can accommodate that set of behaviors and still ensure the safety of the prosthetic and the intact human side while doing real-time planning by using a reachable set. So that'll be the first portion of my talk. The second portion of my talk will be about this sort of Koopman-based control. And in fact, that Koopman-based control has allowed us to do really cool stuff with manipulation-based control. And this is a data-driven method. And the really amazing thing is that this is the first example of a pick-and-place robot that can actually, a soft pick-and-place robot that can actually pick stuff up, figure out its weight, and actually place it into the right bin. And it turns out that we're doing, again, all the control, everything online for this platform. And it's essentially figuring out what the weight of these things are. It's never seen these objects before. And it's essentially able to place them into the right bin, essentially associated with their weight. So that'll be sort of the two things that I'll speak about. Chances are I'll probably only get to speak about the first thing because I have way too many slides. But if you're interested, happy to stick around and talk about the second thing, which is really interesting and associated with a lot of things that are going on at UW at the moment. So reachability-based trajectory design. And what I'm going to do is focus on the context of manipulator-based planning, although this method extends to a bunch of different types of planning algorithms or a bunch of different types of platforms. So typically, when people are thinking about planning for or control for autonomous systems, they usually divide the planning and control into a hierarchy. In the top level, there's sort of this Google Map style planner that's generating sort of turn-by-turn instructions of, how do I get from Ann Arbor to the University of Washington? Well, first step is to get on I-94 and drive, right? The mid-level, there's this thing called the trajectory planner. What the trajectory planner tries to do is to follow that those turn-by-turn instructions. Eventually, that information is passed to a tracking controller, and that tracking controller, may have a model of the entire powertrain, whatnot. And what that's trying to do is to basically track the trajectory that's been generated as best as possible. Usually people do this sort of division of labor because it's really hard to do useful planning over really long horizons when you have models that are extraordinarily complex. And so by breaking it into these different pieces, you can sort of break the problem over different horizons into different model fidelities. So the high-level planner can have a really simple model, the trajectory planner can have a mid-level sort of medium complexity model, and the tracking controller can have a really complex model. The problem is that ensuring safety in this context really means accommodating all of the potential errors that can be created as you go down this hierarchy. And so people have thought about how do you ensure safety in this context, and usually the way that they do it is by trying to ensure some level of safety in the tracking controller. And what that means in practice is that people have thought about developing a variety of different algorithms that can introduce safety at this level by doing some sort of validation. Traditionally, this has been done by essentially just doing some sort of collision check. And the challenge here is, I may generate a trajectory that's discretized in time, and I may try to follow that using my tracking controller. How do I ensure that that continuum, that is that entire trajectory, doesn't actually collide with some obstacle? Well, the first set of methods are called these check methods. And what they do typically is just, I have a precomputed trajectory. I'm just going to verify at runtime that this particular precomputed trajectory doesn't collide with anything. These methods don't actually do any real-time planning. They just are doing verification after the fact. Second class of methods, which I'm going to call correct methods, basically take a particular trajectory and try to modify it. Essentially, they try to modify the control input that's applied to track that trajectory in order to ensure safety. Actually, there's been a variety of methods to do this that have been presented. Reference governors, if you've been following the literature for a while, have been a very popular method for doing this type of stuff. Recently, sort of control barrier functions, and I think you're going to have Aaron Ames come and speak. He'll probably talk about this. It's really cool stuff. You get it working for a variety of different systems. And then the last set of algorithms are these things called fast track. Again, so these are all sort of the same philosophy. They think about trajectory planning and control in slightly different ways. So the reference governor and control barrier function methods essentially assume that some sort of trajectory plan has been handed to these methods a priori, and they just try to greedily make changes to that trajectory by modifying a control input in order to ensure safety. And that can mean that sort of you get greedy behavior out of them because they're only seeing sort of modifications at the particular instance in time that they're looking at. Fast track is really interesting because it can actually allow you to think about a horizon of trajectories. The problem is that the way that fast track works is it treats the trajectory planner as if it's a disturbance. And so it solves like a Hamilton-Jacobi-Bellman style equation a priori that it uses at runtime. And by treating the trajectory planner as a disturbance, it can be unnecessarily conservative. And I'll illustrate that later on in the talk. So more recently, lots of people have been thinking about bringing in safety at the trajectory planner level. And in fact, there's sort of been two methods. The first is these funnel library methods that, again, you had Russ in here a while ago, but his student Ani Majumdar, who's now a professor at Princeton, has developed. These methods are really cool, but the way that they work is by discretizing essentially and having a finite set of trajectories, and you select between them. And essentially, the collision check is by just looking at discretized time instances, and that can sacrifice some notion of safety. What we're going to talk about here is reachability-based trajectory design, which is an algorithm my students and I have developed. It can actually operate over a continuum of parameters or a continuum of trajectories rather than just a finite number. And we actually have a way to ensure safety over all time, not just at finite instances in time. And the really cool thing is we figured out a way to actually extend it to sort of higher dimensional models in a really nice way, which is what I'll talk about today. So how does it work? Let's look at this fetch robot on the right-hand side. Well, what we're going to do is introduce a set of trajectory parameters for those fetch robot. Those trajectory parameters are essentially going to describe different possible motions for the arm. What we're going to do then is think about a continuum of trajectory parameters, and that's going to be associated with a continuum of different behaviors in the workspace of the robot. And in fact, at runtime, what we're going to do is basically pre-compute this reachable set. And then at runtime, we'll have an obstacle that appears. And that obstacle is basically going to eliminate a set of trajectory parameters. These are going to be associated with the obstacle. Essentially, we'll generate an outer approximation to that set. And in practice, then, if we're given a particular desired state or some sort of cost function, well, that may be associated with some goal state over here on the left-hand side. And in practice, what we'll do is solve this optimization problem down here on the bottom left. And it'll turn out that this optimization problem can be written down in a fairly nice way, which will allow us to do real-time planning. The two takeaway messages here are we can do it sort of for high degree of freedom robots, and we're generating a reachable set, and it's for a continuum of trajectory parameters. This is done offline. And online, we can do obstacle discretization for real-time validation, and I'll describe what that means as we go through the talk. So let's talk about the theory of how this works. So again, I'm going to focus on the manipulator model. If you take a look at the papers that I mentioned earlier in the talk, we've actually extended it to a bunch of different systems, but then the manipulator models allow us to talk about how to extend these ideas to higher dimensional systems. So to do that, we're going to start off with a few assumptions. So we'll assume that we have a bunch of joints here, and each of the joints is going to, have some actuation associated with it. And so we'll denote, joint I by QI, that is the trajectory of joint I by QI. And we'll write down the equations of motion as follows. And for the sake of simplicity in this talk, I'm going to make two assumptions. It'll turn out those two assumptions can be removed in general, but it'll simplify exposition here. The first assumption I'm going to make is that all joints are revolute. It'll just allow us to write down some matrices in a nice way, but in fact, that isn't a strict requirement. The second assumption is that the model is fully actuated. As I showed earlier, we've gotten this working on walking models that are actually under-actuated, so it'll turn out that this technique can extend. But we'll focus on the actuated case in this case. The really important thing is that if the model is fully actuated, and what that allows us to do is to track an arbitrary trajectory with a bounded tracking error by using something like feedback linearization. And in practice, if we start at the same initial velocity as the desired trajectory that we want to try and follow, then as long as we satisfy actuation limits, we can actually track that arbitrary trajectory perfectly well. That is assuming that we have a model that is perfect. So what we're going to do now is talk about how we parameterize trajectories of this arm. And we're going to make one assumption. That is, we're going to assume that one of the trajectory parameters actually corresponds to the initial velocity of the arm. The reason that that is useful is, again, if I know what the initial velocity of the arm is at a particular runtime, and I have a desired trajectory that matches up with that initial velocity, well then, as long as I satisfy actuation limits, I can track arbitrary trajectories by using something like feedback linearization. The rest of the trajectory parameters can be arbitrary. In this instance, I'm describing it as just some sort of velocity, but in fact, or acceleration, but in fact, it could be anything. As long as I have this joint velocity at time 0 as part of my trajectory parameter space. So for example, my joint trajectories could look like this. So I start off at some initial joint velocity, and then I go up to some peak, and then I come back down. Well, as long as, again, I have this initial velocity at time 0 as one of my trajectory parameters, it's totally fine. All of my trajectories are going to be defined over some finite time interval from 0 to TF. And in this instance, because I chose this as my joint trajectory parameterization, it would describe, for example, the acceleration here. And what we'll do, since we're interested in receiving horizon planning, is assume that we have a finite amount of time to plan. So in fact, we'll assume that we have T plan to plan. And what that means in practice is that the robot must find a new plan within time T plan. Otherwise, it continues executing its previous plan. And that's why we've brought our plan eventually to a stop here, because we want to make sure that if we can't find a new plan, then eventually we bring our arm to a stop so that we don't actually keep moving beyond the time upon which we've actually done a verified planning. The last assumption I'll make is I'll assume that the trajectories begin at q equals 0 without any loss of generality. You can just shift your coordinate systems as needed to make this assumption satisfied. So I mentioned that part of the way that we're going to think about planning here is by applying lifting. And the first lift that we're going to describe here is a really simple one. So what we're going to do is I'm going to take my trajectories here, and I'm just going to consider the cosine and sine of those trajectories as functions of time. And in fact, then, if I have a particular trajectory on the left-hand side, K, it's going to describe a particular trajectory on the circle here. And in fact, in practice, if I have a family of trajectory parameters on the left-hand side, well, that's going to correspond to a family of trajectories on the circle. Okay, so I've basically taken my dynamics, which are Q, and basically lifted it by looking at the function evaluation of cosine and sine on these trajectories. What that's going to allow me to do is now consider the joint reachable set of the system as a function of the trajectory parameters. And what that's going to look like is a subset of R2 cross K. I can think of this as S1 cross K if I'd like, but it'll turn out we're generating outer approximations eventually, and they'll actually belong to R2 in that case. So what we're going to do is define this joint reachable set object. And the joint reachable set is going to be defined as me taking my joint trajectories as a function of K, taking the cosine and sine of them, and making sure that the derivatives of them as functions of time obey the parameterization. Okay, so this set Ji is essentially going to describe the sine and cosine evolution of my joint trajectory as a function of time. Now, that's really great. Hopefully, you're sort of seeing where that could potentially be useful. But in practice, we're going to have several different joints. And the important thing here is that I can actually do the same type of computation for each of the joints inside of my robot. But in particular, if I know what the initial velocity is at a particular instance in time, what I can do is look at a slice of this trajectory parameter space corresponding to that particular joint velocity at the initial time. And what I can then do is carve out the workspace of the robot across the remainder of the space. And in fact, I can do that for each of the different joints and describe the workspace associated with each of those different joints. And in fact, I can draw out this really beautiful sort of object in the workspace of the robot. The important thing, though, and we'll call this operation of specifying the initial condition slicing, we'll call the operation of stacking up all of these joints together stacking. And the important sort of takeaway, and what we're going to talk about next, is that by slicing and stacking these simple joint reachable sets, we can actually construct a high-dimensional reachable set of the entire arm. So in fact, if I have the joint, the first joint, Ji, well, what I can do is I can slice in the initial velocity of that particular joint, and then I can generate a rotation matrix associated with that particular joint reachable set as a function of time. And in fact, what I can do then is if I slice, I can multiply that by the link volume, and I can actually get a parameterized swept volume that describes the workspace representation of that link while it's following this set of trajectory parameters with this initial velocity sliced in. Now, I can try to repeat that same exercise with the second joint. Again, I have my trajectory parameterization, and suppose my rotation matrix looked like this for this particular joint. Well, now I can slice in the initial velocity of this joint, and then I would have sort of R2 times V2, which would describe the swept volume of this particular volume as a function of these trajectory parameters. But the challenge is that I'm missing the translation due to the first link, and I'm missing the rotation due to the first joint. Well, the important thing is now I can actually recreate that by essentially first getting to the first or the joint location of the origin of the second link, and then actually bringing in the parameterized sort of joint location, and then multiplying by the swept volume of the second rotation matrix. What that means in practice is that I'm going to have a translation associated with the end effector of the first link, added together with the rotation volume of the second link. And in fact, I can represent that in a really nice way by looking at this operation here, R1 times R2 times V2, plus R1 times P1, where P1 is the end effector of the first link. And in fact, what that allows me to do is essentially stack to get the swept volume of the second link, and slice to get the initial velocity and associated sort of parameterization of the rotation matrices of the associated links along the way. And I can repeat that operation as I go down the link arm. And what that allows me to do is essentially account for the initial joint angles and velocities by using stacking. And then I can compose these reachable sets together by using this stacking operation in order to actually get the entire swept volume of the arm as a function of this trajectory parameterization. What that means at runtime then is if I have this obstacle, I slice in my initial velocities, then I stack to get my entire swept volume as a function of those trajectory parameters, have these obstacles, I can essentially intersect them with this swept volume and essentially identify a safe trajectory parameter that gets me as close to this goal as possible by performing some sort of optimization. And that's what I'm going to describe next. Okay, so slicing stacking allows me to generate a high-dimensional reachable set. But how do we compute those reachable sets? How do we implement stacking and slicing? And how do we generate the hard constraints that are associated with safety? That's what I'm going to talk about next. But before I do that, any quick questions? Okay, I will take that silence as confusion. Okay, so what we're going to do is generate these reachable sets for each of the joints using zonotopes. So if you've never seen a zonotope before, the zonotope can be described by a center, C, plus generators. Okay, and these generators can be just arbitrary vectors in Rn. And we can generate a zonotope by essentially allowing these generators to be multiplied by an interval. And by adding these things together, we essentially get these rectangular looking objects in Rn space. Okay, so the cool thing is, if I want to compute a joint reachable set, the impressive thing is that I can generate that by using existing tools like Cora, which has been developed by Matthias Althoff's group at TU Munich. And essentially what that can do is generate a reachable set, a joint reachable set that looks like zonotopes in this space on the right-hand side. And what we get are a finite number of these zonotopes that are describing the behavior of the reachable set over each of these time intervals. Okay. And the impressive thing is I can describe these zonotopes as generating an outer approximation to the true joint reachable set. And in fact, we can prove this following theorem, which is this zonotope approximation to the joint reachable set is actually an outer approximation to the joint reachable set. And that's really useful for us because if we want to say something about safety, well, we can say something about safety here by using this outer approximation and ensuring that this outer approximation doesn't run into anything. This outer approximation doesn't run into anything, then it means that the original joint reachable set doesn't run into anything. So the next question is, how do we actually slice in at runtime? And it'll turn out that slicing is no different than me fixing a particular zonotope coefficient to a particular value. So what that means in practice is that I would set a particular generator to a specific value. And what that means in practice is that I'm actually generating a slice of the zonotope here. And in fact, at runtime, if I fix a particular zonotope coefficient, it corresponds to us fixing a particular initial velocity. Okay, and so in practice, if I fix that initial velocity, well, that's going to correspond to me selecting out a specific slice of these zonotopes as functions of time. The cool thing is, I can essentially do the same thing to generate matrix zonotopes, where now, instead of having these objects in Rn, I can allow these G1s and Cs and GIs and Cs to be matrices. So in practice, what that's going to allow us to do is that if I select a particular slice here and I have a link volume V1, what I can do is I can take the joint reachable set and treat it as one of these rotation matrices by simply transforming the zonotope into a matrix zonotope by just reshaping the joint reachable set into the associated matrix rotation. In fact, what that would mean in practice is that if I then multiply that matrix by the link volume, I'm actually getting out the swept volume as a function of time. The cool thing is you can actually prove that these matrix zonotopes for each link over approximate the rotation matrix set. Okay, so if you have that joint reachable set that's an outer approximation, you can get the similar property for these matrix zonotopes. So now in practice, what we can do is essentially, if I have a particular end effector location, well, I can figure out what that end effector location is as a function of the particular trajectory parameters that I've chosen as a function of time by basically applying this matrix zonotope operation to the end effector of that first link. And that allows us to get the translation, that allows us to describe the beginning of the second link by using the first link's end. And in fact, we can repeat that same operation to essentially allow us to consider or construct the swept volume representation for the second link by just doing this type of matrix arithmetic. Okay, so we have the rotation component and the translation component. We usually call these rotatotopes because we like fun names, right? And these fun names allow us to understand what these objects are actually representing in practice. It is the representation of the swept volume in the workspace of the robot. In practice, again, these rotatotopes can be sliced to get zonotopes containing the swept volume. And what that means in practice is that now I get these sort of swept volume representations that actually look like zonotopes. And in fact, this collection of rotatotopes is a parameterized swept volume. And what that means in practice is now if I want to actually do collision avoidance, I can describe collision avoidance in sort of two steps. The first step is I slice in my initial velocity. And then I have an associated set of possible things that the arm can do beginning from this initial velocity. And any value along this line here corresponds to potential things that the arm can do. I'm showing one potential thing that the arm could do at a particular instance in time. And now, if I want to ensure that I'm safe or detect if I've collided with anything, well, I just need to do zonotope intersection if my obstacles are represented as zonotopes. And in order to do that, you need to understand how zonotope intersection works. It turns out that two zonotopes have non-trivial intersection if you can describe the center of one as being inside of this new zonotope that's been created. Okay, so that is Z2 with the Minkowski sum of the generator of the first zonotope. So what does that look like in practice? If I call this one Z1 and I call this one Z2, what I can do is basically take the generators associated with Z1 and essentially add them to the other zonotope and essentially see if the center of the first zonotope actually is actually belongs to this new zonotope that I've constructed via Minkowski summing. And in fact, that operation, as I'm illustrating sort of here, can be described in a really nice way as the max of a set of linear constraints, and that's what I'm going to show next. So see this. So I can actually represent this zonotope over here, the one in gray, as a linear constraint. And in fact, I can describe collision avoidance of this over the max of a set of linear constraints. So if the max over a set of linear constraints is less than 0, then actually this trajectory parameter is safe. And the cool thing then is that I can write down this optimization problem as just the following. So I'm minimizing over some cost function that's a function of my trajectory parameters, and I'm essentially ensuring that I satisfy this max constraint written down here. And the impressive thing is that this can be cascaded to build out a full arm, and this can allow us to do really nice optimization at runtime. And I haven't described how self-intersection and joint limits work, but in fact, they can be described in a similar form. Take a look at this RSS paper, and it'll walk you through all the details of doing that. But it's even simpler than the sort of Minkowski sum style of operation that I've described thus far. So in fact, we've done this on a bunch of different platforms. I was showing some at the beginning, but here's another example on an arm. Here, the goal is to get this fetch arm to the top. Note that this is usually really hard for planning algorithms because this obstacle here, which is the table, is really small. So it tends to be really hard to actually do planning through this type of obstacle. You're going to see, and I'll pull this up. OK, so what we're doing here is we have this goal configuration up here. In black, eventually, you're going to start seeing the high-level planner, which is an RRT in this instance, just generate plans or waypoints that are essentially in collision repeatedly. Nevertheless, this zonotope construction is going to be able to find a way to navigate its way out of these sort of in collision configurations and get to this goal configuration. So in black, you see some of these are in collision, but the arm is still figuring out, hey, I need to get to these waypoints, but not be in collision. And eventually, you're going to see that this arm is going to figure out its way to get over the top here. OK, so this is done in 4x here, but all of our code is available here. Take a look. I mean, the optimization bit is actually running really quickly. It's the waypoints that are a bit of a problem here, and that's why it's taking a little bit longer than we'd like it to. But nevertheless, we'll see we've actually been able to do it for a bunch of different situations, like these sorts of situations where we have these sorts of dynamic obstacles appearing. And again, this is all happening in a receding horizon way. So it detects this obstacle, and then it runtime makes a plan to get around that obstacle. As I mentioned, we've actually been able to do this for a variety of different platforms, mostly ground vehicles, but quadrotors as well, as I showed at the beginning of the talk, and more recently walking robots. And we've done a bunch of comparisons to lots of different algorithms here, like nonlinear model predictive control, just running RRT sort of naively, doing state lattices, doing linear NPC, doing fast track, which was that sort of Hamilton-Jacobi-Bellman based equation approach, CHOMP, which is something that's been popularized by Sid Srinivasa. And sort of consistently, our algorithm is usually able to get to goals, meaning get to desired locations at a clip that is better than or equal to its competitors. It's always safe, which is really important. And it never, it's able to sort of, not do it without being so conservative that it becomes cumbersome in reaching these goals. These are a bunch of different platforms here. These are ground vehicles. This fusion model is actually a really complex vehicle model that we have. We're working with Ford to actually put this algorithm on their self-driving cars. As I mentioned recently, we've actually been able to get this type of stuff working on CASI, but it hasn't been published yet. So I won't talk too much about that other than showing that video. And now I'm going to switch gears and start talking about Koopman-based control. But I realize that I'm already sort of at 2:15 here, or I should say 11:15. So maybe I can pause and take some questions and then maybe show some videos of how this Koopman-based stuff works and then stop there. So any questions about this sort of reachability-based trajectory design approach to planning?
If anybody wants to ask any questions, you're welcome to type things in the chat or raise your hand or just unmute and speak up. Ram, one question that I just realized somebody had messaged me privately on chat.
Okay.
Maybe it would have been better if I'd interjected this earlier, but can you quickly define reachable set?
Oh, good question. Okay. So a reachable set is basically going to correspond to, in this instance, and actually let me pull back here for a second. So let's take a look here. It's maybe a good slide to look at. So the reachable set in this instance is going to be essentially the set of cosines and sines as a function of a trajectory parameter that I am able to achieve while satisfying my dynamics at a particular instance in time. So in this instance, it's basically like things that can be reached by the dynamics at an instance in time and over the finite time interval that I'm considering. Hopefully that answers the question. Any other questions? Okay. If not, I can jump ahead to this Koopman stuff and sort of talk about it pretty quickly. The first thing to keep in mind is soft robots are extraordinarily difficult to model, and the challenges are because you get these sort of continuous deformations. They have distributed actuation. They have these nonlinear material properties. The good thing about soft robots is they are, you can get hit by them and they don't really hurt that much. And the damage that they can cause is not so bad. So this is my student Dan, who's now he just finished his PhD, is working with Rob Wood now. The problem is that controlling these kinds of systems can be really hard. But the good news is they're fairly safe. Like you can have them run into things. They're not going to damage things. They don't hurt if they hit you. I've been hit by them a bunch. It's not too bad. What I'm going to talk about in this section is this approach to doing data-driven sort of modeling, and that is going to allow us to do convex control. And in fact, we can actually do real-time control even with loading that's not necessarily built into the model while doing data collection. The idea here is the same thing actually that we did earlier, which is we're going to do lifting here. And the idea for lifting is that if I have an original space down here, maybe I want to do something like classification. Well, down here, if I have these red points and blue points, it's pretty easy for me to run like an SVM and separate these two pieces of data. On the other hand, if I have data that looks like this and I want to run a linear SVM, well, this data is in a circle, like this red stuff is in a circle, and finding a separating hyperplane that separates the red points from the blue points seems really hard. However, if I do this lift and I transform the data into this paraboloid shape, it's actually really easy to find a separating hyperplane, right? And what we want to be able to do is the same thing to our dynamics. If we lift our dynamics here, maybe they look nonlinear down here. Can we lift them and make them look linear up here? Actually, that's what we did with the arm. So when I had that arm, the rotation matrices were actually really complicated looking. But in fact, by looking at the sines and cosines of them, I actually was able to write down a linear time varying system. It turns out that linear time varying system, which I computed the joint reachable set for, was actually really nice for me to construct a Zonotope-based representation for its reachable set using Quora. So in fact, we're going to do the same type of trick here. We're going to use Koopman operators to do it. And maybe someone has given a talk about this already at UW. I wouldn't be surprised, since Steve Brunton and others are there working on this kind of stuff. But the idea is, if I have a nonlinear system like the one on the left-hand side, I can describe these nonlinear dynamics, can also describe a flow map for the system. On the right-hand side, I can consider its evolution here. And its evolution could look something like this, right? Well, what I'm going to do is construct this Koopman operator, which is going to be describing the evolution of functions according to the flow map. And what that's going to allow us to do is essentially consider sort of this function space up here and consider the evolution of the evaluations of this function along trajectories of the system. And in fact, that Koopman operator, which I can construct on the left-hand side, is actually going to be linear, but infinite dimensional. The challenge is, of course, building a finite dimensional approximation that's good enough for you to actually be able to do control. And in fact, that's what this work is about. And what we've been able to do is essentially construct these really nice representations for these Koopman operators. And in practice, we can build these sort of nice matrix representations for these Koopman operators as they act on function basis. And in fact, what we can do is apply linear regression to actually construct these Koopman operator approximations. And the way that we've done this is by basically appending the control input to our basis functions. And that will allow us to identify a Koopman operator by using just something like regression. And in fact, by doing this kind of appending, we can actually identify LTI models of these systems. And those LTI models are going to allow us to do real-time control. And in fact, what we've done in this RSS work is actually shown how to build sparse approximations to these A and B matrices that are going to allow us to do MPC-based control in real time for these soft robots. And in fact, we've applied it to a bunch of soft robot systems. This is sort of an illustration of how it looks. This is not using any model of the trajectory a priori. That is, it is identifying what trajectory it should follow at runtime using this Koopman operator-based representation. So the Koopman operator representation is not doing feedback about that trajectory. It's actually, finding that trajectory at runtime. And in fact, we've done a bunch of different comparisons and whatnot. And this is sort of how it looks. The really cool thing, as I mentioned, is you can actually extend this work to actually accommodate loading and lifting of objects and whatnot. And the way that that's done is by simply sort of adding the weighting as an additional sort of lifting function. And in fact, that's going to allow us to do sort of, a Leuenberger style observer to actually identify what the weight is at the end effector at runtime, because everything is nice and linear. And that has allowed us to actually build sort of the first soft manipulator that can actually do pick and place in a really nice way. And again, the really cool thing here is we've identified the model by using these sort of data-driven techniques, using the same sort of lifting philosophy that I applied in that RTD style thinking, but now to actually doing Koopman operator-based control for these types of soft robots. And actually, we've gotten quite a bit further. This was at the beginning of the year. We've actually been able to do some fun stuff that hopefully you'll see some videos of soon, where we're actually been able to do things like throw objects and play catch with, with a dog. So in short, this is sort of the two pieces of the talk here. These are the students who are actually doing all the hard work. These are our sponsors. We've actually want to make this as easy as possible for people to use all the stuff that we're doing. So go down here, take a look at our GitHub stuff. This RTD tutorial on the left-hand side is for all the ground vehicle things. This is for the arm work. And this is the soft robot Koopman stuff that people have been playing around with more recently. You can take a look at all that. We actually even have Quadrotor stuff. I haven't thrown up the GitHub link there, but it's very similar to these links down here, and you can find it off our webpage. The takeaway is that this RTD approach allows us to do sort of collision-free planning. We can do lifting to allow us to do convex control design for soft robots. And these are sort of all of the coding links that are available for people to play around with if they're interested. And that's all.
Awesome. Thanks so much, Ram. That was a genuine tour de force.
It's a lot of stuff.
What questions do folks have? Joey, I see you unmuted.
Yeah, I have a quick question about the RTD method. So at several points you highlighted that like the planning is done based on a slice taken at a particular velocity. And so I'm wondering like, how do you see these methods scaling to maybe like more dynamic behaviors where like there might be large joint velocities or potentially even like errors in what the estimates of what the joint velocities are, the momentum in the system?
Totally. So to clarify, we're slicing in the initial joint velocity. So it's just at the initial time of planning. So like when you start planning, what was your joint velocity at that time? In terms of like model inaccuracies, that's a really good question. In fact, almost everything I've described here can extend to accommodating modeling error. So like I haven't described that here, but in fact, these Zonotope-based methods and manipulator planning in general, you can generate really nice error bounds for when you actually have error that arises from modeling inaccuracies while actually building these sort of tracking controllers. So it's a lot of the beautiful work that came out of sort of the 80s and 90s in manipulator planning and control. The thing is that you can then actually append those modeling errors as essentially inflations or expansions of the zonotopes that you generate. And those zonotope errors can be, functions of time. So in fact, you can add these sort of nonlinear sort of scalings of the zonotope. And actually we've done that for the walking models.
Yeah, great answer. It was awesome talk. I was very pleased to see it.
Awesome, thank you.
Another question that I think only came to me on chat is about collision avoidance. Do you handle only one obstacle at a time, or can you handle multiple obstacles?
Yeah, so actually we can handle multiple obstacles. So all these examples up here at the top of the talk. So like down, in this videos, let me pause here. So like, these are multiple obstacles that are all sort of treated independently. So in practice, in fact, for the ground vehicle work, you don't actually need these obstacles to be represented as zonotopes. They can be arbitrary points. You can have these, you can represent non-convex obstacles in the manipulator work as like unions of zonotopes. None of that is a problem. And so that's all doable. And in fact, is what we're doing in these examples, even in this Quadrotor example. All these obstacles like this one over here on the left-hand side and this one up here are both being treated at the same time as like obstacles that you need to grapple with. And in the manipulator work, in fact, it's actually thinking of all of these obstacles sort of together at this instance while it's doing planning.
There's another question on the chat asking about justifying the choice of Koopman observables that you're using when you augment your state space. I'm interpreting that to mean, why did you choose those observables? What if you had chosen others?
Yeah, that's a really good question. So I actually didn't even spell out quite what we're using as observables here, just because it's actually fairly open for us. We've actually done this work here. And let me step back here for a second, if it'll let me. Okay, so when we did the Koopman work, we've actually done it with a bunch of different basis functions. So, we've done, monomials, sinusoids, radial basis functions. We've actually, our code that's available can take all of those, whatever basis function you can basically think of, we have implemented essentially. We're not really seeing that drastic of a difference between those different basis functions representations. What I will say is at the moment, these types of motions that we're playing around with are fairly benign. So like, meaning we're not really moving that fast. And so these sorts of, I will call them sort of linear projections of the Koopman operator, they're okay. They do really well with respect to these sorts of tracking problems. But on the other hand, if we want to start doing more dynamic things like throwing, these sorts of linear projections tend not to be as good. And so Dan and I have a recent paper on arXiv where we actually built a slightly different class of projections that's bilinear and actually use those bilinear projections while still doing real-time control in a nice way. And that has allowed us to do more interesting things. in terms of being able to do dynamic things. The thing I'll say is the basis functions we've chosen have not been as serious of a problem for us as opposed to the types of projections we're considering here of this Koopman operator.
Other folks have questions. I guess I have maybe a related question. Can you say more about, I mean, it's really neat that you're able to learn to manipulate this continuum, robot using these methods directly from data. Can you say more about when you, what kind of system you expect this to work for, and what kinds of situations you expect it to fail in?
Yeah, so it certainly fails in the instance we're doing these sort of more dynamic operations, right? So the thing we're doing here, and it's sort of buried in here, and maybe that was the question that Ashwin was asking. So, in practice, when we do this kind of selection here on the left-hand side, where we're basically stacking together sort of these positions and then, or velocities, and then the inputs as sort of separate basis elements, we are sort of restricting the class of Koopman operators we can actually identify or build. And that may not necessarily converge to the true dynamics of the system in the way that Koopman operators are known to. So in fact, really you would need to basically consider lifting both the state and the input, or both X and U in this case, and then identify a Koopman operator. The problem is that you wouldn't be able to identify an LTI model in that situation. And so the challenge in this instance is that these LTI models are really useful for doing real-time control, but they may not necessarily be accurate. The good news is, at least in this sort of slow-moving soft robot world, this hasn't been too much of a problem. Like, these class of models tend to be good enough for us to actually be able to do the things we care about. However, when we do more dynamic things, we need to lift in a slightly more strategic way, and we've already sort of identified that as a pain point. The good news is, at least these bilinear models seem to be good enough to grapple with that problem, but more information hopefully will be learned as we keep playing with these things actually in lab.
Cool.
Mm-hmm.
What other questions do people have? I can keep on going selfishly. Again, if people have questions, you can feel free to unmute. You can raise your hand. You can type into the chat. So Ram, maybe a more general question. There's a bunch of lot of students on the call because we have this as a colloquium for credit. And so just regarding your general theme of these techniques that take a very concrete real world, or like in the lab problem, real devices, real robots, real vehicles, and then lifts to infinite dimensions. This is like a common strategy in math, but not necessarily so common in engineering so far. So like, what recommendations do you have for folks who are intrigued by this idea and want to learn more? Like what readings, what courses, how do you train your students to do this kind of work?
Yeah, that's a really good question. So in general, I mean, these lifting approaches are really sexy. And that's when I first saw them, in graduate school, they're really appealing because they seem to transform any nonlinear system into something that looks linear. And hopefully people recognize linear seems really good, right? And in fact, there was a variety of different people in the 60s and 70s who were really excited by these approaches because they could essentially transform any problem that you care about into something that looks convex and linear. And that meant that you could solve like these really complicated optimal control problems as convex optimization problems. You could transform dynamics problems into things that look nice. The challenge has always been that it's like infinite. And so infinite dimensional objects, like how do I actually put that on my computer and do useful things with respect to? The good news is that more recently, people have been recognizing that maybe I don't want to think about this for safety, but I just want to think about building these operators for other reasons. In that case, like maybe building finite dimensional truncations of them is good enough to be able to do something. On the other hand, like the compelling thing about sort of the first portion of this talk is that essentially we could build these outer approximative representations of lifted dynamics, and that was actually really useful for us. So when I was looking at sort of this joint reachable set thing up here, the really cool thing was that essentially I was generating an outer approximation to the true behavior of the lifted dynamics. So if you can build these sorts of outer approximations, then you can say something about safety, but it's saying you need to approximate the behavior from the right direction. And that's been sort of the really exciting thing that, I could say that I've been working on for the past several years, is how do we build these outer approximative objects in useful ways? We've done that with a variety of different techniques. These Zonotope ones are a nice way to do it for kinematic chains, but for ground vehicles and other systems, there are other ways to do it using semi-definite programming or other techniques. So to answer Sam's second question about like, hey, what classes do you take to be able to do this kind of stuff? You need a bunch of analysis and functional analysis and that kind of stuff. And so it's really helpful to understand how duality works and how function spaces work in order to really be able to sort of richly think about some of these ideas. But at the same time, it's helpful to think about sort of the numerical methods that people would need to be able to apply these types of algorithms. So if you have a numerical methods course, or if you have a course that teaches you about convex optimization, so I'm sure that is a popular course at the University of Washington, I would, semi-definite programming, these kinds of methods, though I didn't speak about it here, are really nice ways to build this type of relationship into an approximation scheme.
Cool. Yeah, and for the students that are enrolled, if you, I'll try to gather some of these pointers to specific UW courses and pop them on the Canvas page for folks if you're interested. Cool. We're getting over our allotted time. Any other questions? Now's your chance.
Right.
Okay, cool. If we're winding down, people are taking off, then Ram, thanks again for taking the time and showing us the super cool stuff.
For sure.
It's always a pleasure.
Thanks for having me.
Yeah, of course. Be well.
You too.